So, on behalf of my team, I would like to thank you for attending our WARP reactor concept presentation. Also, please be advised that a version of this talk and companion paper are scheduled to be presented at the 2023 IEEE Pulse Power Conference later this month, and respective longer journal articles were submitted to the preprint online physics archive and physical review accelerator and beams, along with the version I've uploaded here just for completeness. Full disclaimer, all errors and conjectures are mine and mine alone. Please do not hold my esteemed colleagues accountable for my mistakes and outrageous claims. So our agenda will be as follows. I will initially introduce my Team WARP colleagues, then provide our motivation and novelty of the WARP reactor, along with its strategic importance. I will then go over relevant warp physics, pulse power technology, and overall reactor concept. We will then review the warp machine metrics and operation scenarios, followed by modeling and simulation results for target parameters, and finally conclude with a summary and Q&A session if space-time permits. So presently, Team WARP consists of 6 primary individuals with over 100 years of combined education and professional experience in pulse power plasma and accelerator physics R&D. From field reverse configurations and charged particle beams for driving controlled thermonuclear fusion to lightning EMP simulators, directed energy weapons, and next generation accelerator technology for flash X-ray and neutron radiography, dynamic object interrogation techniques, and combined magnetic and inertial fusion devices. I am the principal investigator with expertise in the pulse power based accelerator and plasma physics. Dr. William Steigar is our resident distinguished scientist with expertise in pulse power modeling and simulation. Dr. Anthony Link leads our multi-physics modeling and simulation group. Mr. James Kurt Walters leads our pulse power design and engineering team. Mr. Enrique Anaya is our lead controls and diagnostics technician. And last but not least, Mr. Donald Max is our pulse power assembly and operations technician. So the warp reactor concept promises orders of magnitude increase of intense ion beam energies and respective radiation yields at a fraction of the size and cost over existing Z-pinch class accelerators, allowing the economically viable study of new relativistic high energy density, or RHED, physics regimes for probing the intersection between general relativity and quantum field theory. For instance, warp, Unruh, and Casimir effects, along with game-changing direct applications from rep-rated magnetized liner inertial fusion, or MagLIF, devices for energy production and advanced propulsion, to multi-pulse compact flash X-ray and neutron radiography sources for assessing our nation's aging nuclear weapons stockpile. Of particular interest to this conference may be my following conjectures on how we may be able to enhance space-time curvature coupling via 1. The multi-layer red plasma and charged particle ring confinement of terahertz radiation to create plasma ring metamaterial effects. 2. Azimuthal acceleration beyond Unruh threshold of the red plasma and charged particle rings to generate Leidenfrost-like vortex layers, which create space-time phase transition. And 3. Implosion beyond the Casimir threshold of the red plasma and charged particle rings to generate internal negative energy densities, which also provides additional confinement mechanism to the generated 5,000 or more Tesla magnetic fields in order to prevent plasma ring metamaterial rapid disassembly. WARP achieves this dramatic performance boost by using a novel warp core which injects 2 tubular ion beams from opposite ends of a double-barreled dense plasma focus, or DPF, head through magnetic cusps to form co-rotating ion rings which merge near the midplane of the device and are subsequently radially compressed and azimuthally accelerated up to 1,000 times the initial ion beam energies during the properly timed DPF plasma liner implosion. Two DPF and ion ring Marx generators, or IRMGs, heads with embedded reflex triodes are implemented to dramatically reduce the size and cost of the drivers and increase ion ring capture efficiency, along with the added benefits of favorable magnetic field line curvature throughout the implosion process due to the higher velocity, shear stabilized pinch flows near each gun muzzle and greater tuning capability for properly timing the implosion and ion beam generation, injection, compression of the two colliding, subsequently merged ion rings onto a solid or high energy density plasma target. WARP directly aligns with the DOE and the NNSA missions and core competencies as an economically viable and climate-friendly rep-rated MagLIF device for nuclear fusion energy production, as well as a multi-pulse compact flash X-ray neutron source for assessing our aging nuclear weapon stockpile. In addition to developing the next generation pulse power architectures, this strategic initiative will help to benchmark present high performance computing, simulation, and data science with respect to more disruptive and imaginative ultra intense plasma beam configurations. Finally, WARP's success would fortify LLNL's place at the forefront of the subsequent relativistic high energy density physics revolution and aka space-time metric engineering. The physics behind the charged particle ring radial compression and azimuthal acceleration in the warp core is as follows. DPF plasma liner driven magnetic flux compression creates a magnetic wave which causes charged particle rings to radially compress via the Lorentz force, and due to the conservation of canonical angular momentum and adiabatic flux conservation condition, the charged particle ring azimuthal velocities scale as the initial ring radius to the final radius for a gamma equal to 1. And therefore, the final charged particle ring energy scales as the initial ring energy times the square of the initial ring radius to the final ring radius, or as the initial ring energy times the ratio of the final to initial magnetic field amplitudes. For relativistic charged particle motion in pulsed magnetic fields, gamma varies due to the curl of the electric field, which is equal to the change in the magnetic field with time. The principal formulas used in the WARP reactor conceptual models and simulations are provided here for quick reference, which are the standard plasma physics equations for the number of fusion-generated neutrons, plasma to magnetic pressure, total fusion energy, plasma energy, Bremsstrahlung and synchrotron radiation, scientific and engineering gains, fusion energy for sale, magnetic reconnection, timescales, and plasma and particle beam propagation modes. In addition to the standard relativistic formulas, we also introduce a modified Einstein field equation with a naive quantum gravity addition that may be accessible by the WARP reactor for verification or invalidation of the theory, along with figures of merit such as spacetime curvature, gravitational potential, and frame dragging effects. G mu nu is the Einstein curvature tensor, and T mu nu is the energy momentum tensor. 8 pi g divided by c to the fourth is the energy momentum to curvature coupling constant in vacuum and without quantum gravity effects. S captures the Sarfati plasma metamaterial effects. A captures the Anderson-Unruh-Casimir threshold effects. And according to Sutherland, T hat is the energy momentum operator. Psi and psi star are the initial and final conjugate wave functions, respectively. And the bracket of F and I are the final and initial boundary conditions. With respect to the figures of merit, M is the ring mass, R is the ring radius, I is the ring moment of inertia, and the small omega is the ring angular velocity. And I apologize, there looks like there's some mess up here, but I can send a PDF that has the corrected values here. It's also in the paper. The WARP reactor utilizes tried and true Shiva star-like Tempest Marks modules to drive its dual dense plasma focus head and state-of-the-art impedance-matched Marks generators, or linear transformer drivers for rep rate operations, to drive the dual charge particle beam ring reflex triodes. Shown here is a side view of the full-scale warp reactor, which is about 60 feet long and about 30 feet in diameter. Shown here is an end-on view of the warp reactor, showing the azimuthally symmetric Tempest modules with flexible high-voltage coaxial cables connections to the central core. Shown here is a cross-sectional view of the warp reactor, which consists primarily of 40 Tempest modules and 2 ion ring Marks generators and a central warp core, which I will go into more detail in the following slides. 40 Tempest Marks modules drive the dual DPF heads. Each module is a more robust version of the Shiva Star design with an upgraded 1.2 mega amp rail gap switch, a seismically rated welded frame capacitor assembly, along with a modified high voltage output header for the flexible high current coaxial cable connections. Each Tempest module is primarily comprised of 4 Super Duty rail gap switches, aluminum parallel plate transmission lines, and 24 high energy density capacitors with a total energy stored per module of 260 kilojoules, and therefore for total of 40 module Tempest system of greater than 10 megajoules, capable of delivering 60 megaamps to the dense plasma focus loads. 2 ion ring Marks generators drive the dual reflex triodes heads. For single pulse operation, each IRMG is a 30-stage impedance match Marks generator, or IMG, on steroids, or a linear transformer driver, an LTD, for rapid rep rate operation. The IMG version consists primarily of 30 segmented coaxial return spools, a continuous tapered inner high voltage stock, corona toroid, and 40 bricks per stage, with each brick being comprised of 2 capacitors and a high performance spark gap switch. Each IRMG is capable of producing a megavolt, a mega amp, and a 100 nanosecond pulse to the reflex triode, with a total energy storage for the 2 IRMG system of 2 megajoules. Depicted here is a cross-sectional view of the novel warp core. It's roughly 1 meter long, end to end, and roughly 1/2 meter in diameter. The relatively large red, white, and blue squares situated around the grounded vacuum chamber represent the B insulation, the B seed, and the B cusp pulse magnets, whereas the small blue squares next to the magnets and internal light blue rectangles are the annular DPF and IRMG puff valves, respectively. The Tempest modules attached to the warp core at the DPF collection plate on the left and right end of the device, whereas the ion ring Marks generators connect to the 2 back ends of the dual reflex triodes through the IRMG post-hole convolutes. Finally, the primary warp core and most novel central components consist of the coaxial dual DPF and IRMG heads with embedded reflex triodes. This table, the upper and lower tables show the major pulse power parameters and DPF plasma liner and ion beam ring metrics, along with order of magnitude comparisons with one of the largest ion beam accelerators in recent times, PBFA2. The WARP X prototype is a 1/10 scale version of the full scale reactor, which can deliver up to 5 megaamps in less than 3 microseconds into a DPF plasma liner, whereas the 4-stage prototype version of the ion ring Marx generators can generate initial ion beam energies and currents of up to 400 kV and 200 kiloamps respectively. The bottom table provides a comparison of plasma liner beam and ion ring parameters between PBFA2 and Z and the warp devices, with the 60 megaamp warp reactor machine showing orders of magnitude increase in ion beam energy at the GeV level and currents at the 20 megaamp level at implosion stagnation with a 25% acceleration efficiency. Shown here are cross sections of the warp core at different phases during operations. Phase 1 begins with the creation of the B insulation, B seed, and B cusp magnetic fields to ensure full B field diffusion through the metal structures, along with gas injection via the DPF and IRMG annular puff valves, and subsequent firing of the Tempest modules to initiate dual DPF plasmoid generation, liftoff, and rundown. Phase 2 occurs as the two DPFs begin their run-in sequence and the IRMGs are fired to produce the dual tubular ion beams. Phase 3 is when the DPF's return currents have merged and the dual axially directed ion beams have passed through their respective B cusp fields to begin co-rotating and merged ion rings in the embedded B seed field. Phase 4 is the DPF plasma liner implosion sequence, which provides the necessary flux compression and subsequent ion ring pinch and azimuthal acceleration. And finally, phase 5 is the implosion stagnation phase and relativistic high energy density ring and target interaction sequence for fusion energy production, advanced propulsion, superflash X-ray neutron generation, and accessing the new RHED physics regimes. So here, I don't think it's probably going to play. Nope. We could probably jump out, or let's see if I can pull the movie in. It won't let me, Tim. So thanks, Tim. We can go back to the presentation. Sorry that didn't work out as well as I thought it would, but anyway. So next up, we have to help benchmark our WARP reactors plasma liner implosion simulations. We compared them to the semi-analytical model for magnetized liner inertial fusion, outlined by Dr. McBride at the University of Michigan and Dr. Slutz from Sandia, which can be used to reproduce the general 1D behavior of the MagLIF machines. This model accounts for several key aspects of MagLIF, including the preheat of the fuel, pulse power driven liner implosion, liner compressibility with an analytical equation of state, viscosity, internal magnetic pressure, ohmic heating, adiabatic compression and heating of the fuel, radiative losses and fuel opacities, magnetic flux compression with thermoelectric losses, magnetized electron and ion thermal conduction losses, end losses, enhanced losses due to containment or contaminant mixes, deuterium-deuterium and deuterium-tritium primary fusion reactions for different fuel ratios, and finally magnetized alpha particle fuel heating. Furthermore, in order to facilitate the comparisons between our multiphysics simulations and semi-analytical models, we have created a simplified version of the MagLIF model in Mathematica for quickly optimizing warp reactor performance. In addition to the multiphysics models and simulations, we of course have 3D CAD engineering models with associated finite element analysis for electrical and mechanical stresses, along with circuit models and simulations for the Tempest system, the IRMGs, both the single pulse IMG and the rep-rated LTD varieties, and warp core dynamic loads. Due to resource and computational constraints, this simulation was performed for a mini warp core in the Chicago particle in cell code in hybrid kinetic mode, where the electrons are treated as inertialess fluid using MHD equations for the electron response, while the ions are treated as kinetic particles. The top right figure is a graph of the RB theta, or radially enclosed current, whereas the bottom right image is a graph of the respective plasma density at a specific time, and both as functions of radial and axial positions in centimeters. The left figure, again, is a movie, which I'll have Tim, if you can, pull the warp simulation into view. Of the dual DPF plasma generation, rundown, interaction, and eventual implosion phase. And that's it. So we can go back to the presentation, Tim. Thank you. So this table is meant to capture the magnetic reconnection occurs on sub-microsecond timescales with respect to the dense plasma focus plasmoids characteristics as they propagate through their respective B-cusp field regions, and just over a microsecond timescale for the plasmoids to collide with one another at the midplane of the warp core. This slide shows the various DPF and ion beam propagation mechanisms. The top left figure is the propagation criteria for collective mode, while the bottom left figure captures the dense plasma focus diamagnetic drift mode for this particular parameter regime. The middle table shows the ion beam propagates in the collective mode unless the polarization electric field is shorted by background electrons. Finally, the right table displays the reflex triode and initial ion beam parameters along with final compression and accelerations. Of particular interest for accessing the new RHED regime and space-time metric engineering, the electron ring mode of operation may be capable of reaching final compression radius and accelerations of sub-micron scale and greater than 10 to the 23 meters per second squared. The left table on this slide captures the major ion ring compression and acceleration metrics, while the right side displays the overall fusion and radiation parameters. Of particular note is the final ion ring major radius at final implosion stagnation reaches the millimeter scale, and at GeV level azimuthal energies for all protons, deuterons, and tritons, With respect to the fusion and radiation parameters, the peak X-ray and DT fusion neutron yield reach 3.5 megajoules and 6.6 10 to the 18 neutrons per pulse, respectively, with an overall scientific gain of greater than 19. In addition to the fusion energy and X-ray neutron radiation applications, the WARP reactor is also primed for accessing new relativistic high energy density regimes. The 60 megaamp DPF plasma liner with embedded GeV level ion rings appear capable of reaching thousands of Tesla and subsequently multi-terapascal pressures. Those are the pressures that are found deep inside Jupiter. Due to the dramatic compression and acceleration of the charged particle rings, the plasma liner target interactions may even begin to generate significant plasma metamaterial, Unruh, and dynamic Casimir effects, not to mention copious amounts of synchrotron radiation from electron ring modes of operations. Furthermore, once the charged particle rings become relativistic during the final moments of the implosion phase, the decrease in ring radius saturates as the relativistic mass increases. In other words, flux compression shifts from ring velocity to ring mass, or enhanced space-time coupling. Finally, the WARP reactor may also provide a means for accessing the quantum gravity domain for verification or invalidation of various proposed theories by probing for any space-time curvature or frame dragging effects. Of particular interest to this conference is that WARP may be capable of reaching S and A fields of greater than 10 to the 31, and therefore significant space-time curvature and frame dragging effects. The plasma frequencies can be greater than 10 to the 15 radians per second. Plasma relative permittivities of 10 to the 16 or greater, and energy momentum of greater than 10 to the 17. So in conclusion, we envision the WARP reactor as a more compact, modular, and economically viable magneto-inertial fusion device for energy production, advanced propulsion, and/or super radiant flash X-ray neutron source for dynamic radiographic applications, along with providing access to the new relativistic high energy density physics regimes. The WARP device would fulfill the immediate need for an intermediate level machine for Z-pinch, beam, and pulse power flow studies, along with added benefit of recruiting the next generation of RHED plasma and accelerator scientists and engineers and technicians. Finally, WARP would be an ideal platform for prototyping novel pulse power architectures for continuous rep rate nuclear fusion and radiographic movie operations, thereby enabling us to continue our collaborations across the DOE and DoD complexes, along with forging new private industry partners through our CRADA and strategic partnership programs. Below is a list of present and possible future collaborators, and if you're at all interested, please reach out because there's much to be done. To reiterate, my conjectures of the enhanced space-time curvature coupling mechanism, we have one, the multi-layer red plasma and charged particle rings confine terahertz radiation to create plasma ring metamaterial effects via the Sarfati scalar field. And number two, azimuthal acceleration beyond the Unruh threshold of the red plasma and charged particle rings generate Leidenfrost-like vortex layers, which create space-time phase transition. And three, implosion beyond the Casimir threshold of the red plasma and charged particle rings generate internal negative energy density, which also provides additional confinement mechanism to the greater than 5,000 Tesla magnetic fields in order to prevent plasma ring metamaterial rapid disassembly via the Anderson scalar field. Finally, I leave you with the following Gedanken experiment I call a twisted compression of the Ehrenfest paradox. Imagine you are one of a multitude of elementary charged particles which make up a rotating high energy density charged current neutralized particle ring embedded within an axial seed magnetic field that is radially compressed towards zero radius and azimuthally accelerated to ultra relativistic velocity during sufficient flux compression. According to you and a nearby inertial observer, what happens to the local space-time surrounding said ring vortex at the end of the implosion phase? So thank you again for your attendance and attention.